we're going to be doing analysis. So this is lecture number 1, and this is sourced from Principles of Mathematical Analysis, 3rd edition by Walter Rudin. It's a very good textbook. So today we're going to be talking about two things. One, why real analysis? What's so special about the real numbers? And two, we're going to be talking about sets and orders. So first of all, let's get to the first topic. Why real analysis? Now, of course, this lecture isn't going to be so extensive as to get into the axioms of arithmetic. We're not going to be defining plus, minus, times, and divide. We're not going to be the crazy person who spends 370 pages proving 1 plus 1. We're going to assume that... Yeah, but still, he might have gone crazy that day. We're going to assume that we already have all these arithmetic operations under our boot, and of course that will include exponentiation and logarithms as well by extension, and that we already have familiarity with dividing two integers by one another, hence getting the real numbers. So all real numbers can be represented as the quotient of two integers, where we can write. So just to get some terminology over with, this blackboard bold Z represents the integers. This blackboard bold Q represents the rationals. And this blackboard bold C represents the complex numbers, although we probably won't get into those. And this blackboard bold R represents the most important set, the real numbers. So, why real analysis? Well, as you probably already know, there are some numbers that we can't express as a quotient of two integers, like rad2, or pi, or e. But how do we really know that these can't be expressed as two unknown integers? Like, for example, we can make a set that converges to a rad2 perfectly fine, a sequence. No, cut that. We can make a sequence that converges to rad2 perfectly fine. I mean, we can start with the first digit, 1, then we can go over to 1.4, then we can go over to 1.41, then we can go over to 1.414, then we can go to 1.4142, then we can go to 1.41423, and so on and so forth, right? So, I mean, these are all rational numbers. At the end of the day, you can express them all as just some integer divided by some other integer. 14 over 10, 141 over 100, 1,414 over 1,000, 14,142 over 10,000, 141,423 over 100,000. And in some cases, you can reduce the numbers even further. So, I mean, given that we can express all of these numbers in a sequence that clearly tends to rad2, why can't we express rad2 as a rational number itself? Now, here's a very simple proof. So, this is one of the most classic examples of proof by contradiction. Let rad2 be equal to some two integers quotient. Now, this is one of the most classic examples of proof by contradiction. Let rad2 be equal to the quotient of some two integers m and n, right? So, by definition, this would put rad2 in the real numbers. The rational numbers. So, how can we prove this is false, which is what we're setting out to do in proof by contradiction? Well, let's rearrange the terms a little bit. Multiplying both sides by n, we can clearly get n rad 2 is equal to m. And now, squaring both sides, we can get 2n squared is equal to m squared. And now I'm going to do a little side proof. I want to show that if if m squared is even, m is even. And so, of course, we can assume the opposite. Let m be some integer such that m squared is even. In other words, 2 divides m squared, but m is odd, i.e. 2 doesn't divide m. So, how can we prove that m doesn't exist? Same exact method. Now, of course, we can express every odd number as some even number 2n plus 1, where n is, of course, also some random integer. So then we take 2n plus 1 and square it, right? So this gives us 4n squared plus 4n plus 1 by the binomial expansion. Or just by foiling it out, because it's only second degree. So we obviously know that this, since n is an integer, n squared has to be an integer. So that means this is divisible by 4. And this is divisible by 4 as well. And since 4 is divisible by 2, we know these two parts are even. In other words, we can express this as 2 times 2n squared plus 2n, where this is an integer. But then we have the plus 1 on the side. So at the end of the day, if m is an odd number, then m squared is an odd number, which means that there's no possibility that if m is odd, m squared is even. So that means right here, since m squared is equal to 2 times some integer, that means m is even. Here's the thing. When we want to express rad 2 as m over n, we want to express it in least terms. Now, obviously, we all know least terms is going from something like 3 over 6 to 1 over 2. But to express it a little bit more formally, we want to make sure that m and n are relatively prime. Or that their greatest common denominator is equal to 1. So, we know that m and n have no factors in common. Oh, wait, sorry. So, greatest common factor. Okay. What? Okay. So, is even. That means that we can express it as 2 times some integer k, right? So then m squared has to be equal to 4 times k squared, which is also an integer, which implies that 4 divides m squared. All right, so now we have this equality from before. And if 4 divides m squared, then 4 must divide 2n squared. But that implies that 2 divides n squared. And if 2 divides n squared, that means that n squared is even. But if n squared is even, n is even. But wait a second. Because now, m is even, n is even, but their greatest common factor has to be 1. Even though clearly they at least share one factor bigger than 1, which is 2. So this is a contradiction.
What did you try to prove?
Rad 2 is irrational.
Oh, you did it when you were 2, you know.
Because I memorized it. All right. But this is just a direct approach. Let's see, are there any other blackboards? No. Okay, so I'll have to erase. But this is just a direct approach. So we've tried approaching it directly and we failed. But let's try something indirectly. We all know that if we have two rational numbers, m and n, then no matter how close they are, we can find another rational number, specifically their average.
To call it 2 by contradiction?
Yeah, that is between them. Oh, sorry. Let me do that. Now, here's the thing. We tried to do this directly, but it clearly didn't work. So let's try doing it indirectly. We all know that if we take some two rational numbers, m and n, then their average, which is also a rational number, will be between them. So that means we can always find a rational number in between two other rational numbers. Doesn't take a genius to see this is true. But, oh wait, and this is of course assuming that m is the lesser one and n is the greater one. But what can we do so that this helps us actually prove rad2 is in the rational numbers like we expected? Let's take two sets. All rational numbers such that n squared is less than 2. So this is set 1. And set 2. All rational numbers such that n squared is greater than 2. And obviously these sets share absolutely nothing in common. The intersection of them is the empty set. I think that's the right way. So, since the intersection of these sets is the empty set, that means that there's probably a greatest element in S1. And of course, since it doesn't share anything with S2, that means that this greatest element of S1 is less than the minimum element of S2. But of course, n squared is less than 2 is one of our sets, and n squared is greater than 2 is the other set. So that means rad2 is in neither. So hypothetically, since we have this ordering, we can take the average like we did over here to find the only element that isn't in either of these sets, which is rad2. So hypothetically, the max of S1 plus the min of S2 over 2 is going to have to be rad2, right? Because that's the only thing in the positive rational numbers that isn't contained in either of these sets. All right, so now here's what we're going to do. We're going to prove that these two numbers don't exist. Why? Well, let's do it for one side first.
Go all the way over there because it is
All right.
not so clear.
Okay. So I'm going to erase this. Okay.
It is not the same.
Okay. So let's try to find the max. Okay. So let's try to show that the max of S1 and the min of S2 don't actually exist. How? Well, let's do it for S1 first. We know S1 is the set of all rational numbers such that their square is less than 2. What can we do to show that the max of one set and the min of the other don't exist? Well, what we're going to do is, for example, we're going to set the max of S1 to some number, n. And then we're going to show that there's another number also in S1, let's call it P, such that P is greater than n. And then we can use the same relation to show that there's another number Q in S1 such that Q is greater than P. and the cycle goes on, and there's no real maximum of the set. So, how are we going to do this? Well, it's with one very special relation. Let n be in either of these sets, S1 or S2. Then, let's say we have a new number, m. M is equal to p. Let there be a new number m such that m is equal to n minus n squared minus 2 over n plus 2. And what does this end up giving us? Well, this is equal to n times n plus 2 minus n squared minus 2 divided by n plus 2. Oh wait, I gotta flip this sign. So we end up getting So we end up getting n squared plus 2n minus n squared plus 2. Of course, these cancel out, over n plus 2, which gives us our final answer, 2n plus 2 over n plus 2. So, in short, I'm going to erase all the steps of the proof, so make sure you've noted this down. This is equal to 2n plus 2 over n plus 2. But now I'm going to show you something. Let's say n is in S1, right? This tells us n squared is less than 2. So then what does that mean? If n squared is less than 2, this is a negative quantity. So no matter what the denominator is, because the denominator can never be negative, this is always going to be a negative number right here. So what does that mean? Well, you multiply a negative number with a minus sign and you get a positive number, which means that in reality, if n is in S1, then n squared is less than 2, which implies that m is greater than n, because m is n plus some positive quantity, which goes right over here. So that means that we found some number greater than n in our own set. And of course, we can iterate this again with some number p being 2m plus 2 over m plus 2. And then we can iterate this again with some q being equal to 2p plus 2 over p plus 2. The point is, no matter what number we choose, we can always find some number higher than it. And then, no matter what that number higher than it is, we can always find some number in the same set that's higher than that. And that cycle keeps on going and going and going until we realize, even though these numbers approach something, there's no actual maximum. No matter what we try and declare to be the maximum, we can always find some number greater than that that's also in S1, which disproves it. But what about if our number is in S2? Well, then that means n squared is greater than 2. So that means what's on here is a positive quantity, and this is a positive quantity, meaning this quotient is a positive quantity. And since we're subtracting a positive quantity from another positive quantity, this is going to be less than n. What does that mean? Well, the minimum of S2 does not exist either, because no matter what we try to declare it to be, we can always find some number lower than it, and we can always find some lower number than new low, and it can just keep going. So eventually, we realized that the max can't exist because we can always find some number greater than it in the same set, and the min can't exist because we can always find some number lower than it in the same set. So that means that these two can't exist, and our search for RAD2 in the rational numbers has failed. So that's exactly why working with the rational numbers isn't enough. So we've answered the first one of our objectives. Why real analysis? Why not just rational analysis? Because even though we can always find some rational number between two other rational numbers, no matter how close they are,